Critics will argue that these examples of emergence are illusions and that ultimately everything is epiphenomenal except the laws of quantum physics. To be sure, reductionist theories have been able to predict previously unknown phenomena such as antimatter or black holes. In these cases, the theory is able to shortcut the effort of waiting to see how the universe will evolve. Instead, equations or computer models can quickly give the answer without having to run the system to see what will unfold. We call this calculation reducible computation. But, as has been noted, reductionism has failed to explain emergent phenomena. Moreover, every attempt to derive the second law from Newton's laws, arguably the simplest reversible laws, has failed spectacularly. But if we look at the universe around us, emergent behavior appears everywhere. At the quantum level, gravity is non-existent, and yet at the planetary level, it is the dominant force. In the early conditions of the Big Bang, there were no separate forces, rather the strong force emerged along with the electroweak, then later the electromagnetic force emerged. If we look further afield, we see other emergent behavior. Dark energy seems to emerge at galactic scales, and even further out, we now see dark energy emerge at ever larger scales. No theory has been able to predict any of these phenomena. Even when we know about the laws of chemistry, no lower-level theory is able to predict those laws. The same with biology, evolution, human culture, and so on. If emergence were merely an illusion, then reductionism must hold true, and every phenomenon, no matter how complex, should be predictable and explainable through reducible computation. Yet the intricate tapestry of our universe continues to defy such simplicity. At the heart of emergent behaviors lies a fascinating commonality: phase transitions. These transitions mark the boundaries where systems shift into entirely new states of being. When we map the trajectories of such systems in phase space, we often see discontinuities, jumps, bifurcations, or other unmistakable indicators of transformation. A classic example is the Belousov-Zhabotinsky reaction, which not only showcases a phase transition but also exemplifies a far from equilibrium, adaptive, dissipative structure, a concept we'll explore further later. Consider the everyday phenomenon of water draining through a sink. As it flows, vortices emerge, a clear phase transition where the particles organize into a new, structured state. Similarly, when water freezes, it undergoes a phase transition from liquid to solid. Yet if we zoom in to observe individual water molecules, the iceness disappears. There is no molecular level indication of whether the water is ice, liquid, or gas. The higher order structure, the essence of ice, only manifests at the macro scale. Phase transitions are the signature of new phenomena coming into existence. And intriguingly, during these transitions, randomness often plays a pivotal role, giving rise to novel, unpredictable patterns that could not have been foreseen from the system's prior state.